objective with this video is to provide the information about B time, which is called moment ratio, moment versus curvature, and effective section modulus. Now the first we talk about the moment ratio. The moment ratio is concept that appears in the flexure torsional buckling, and that is abbreviated at FTB. Now moment ratio has a relation with single curvature and double curvature. I explain it here what is single curvature and double curvature. If we have a frame like this one and the frame is loaded on the various loading, the blue color one is the deformed shape, and you can see the one that is columns, it has a sagging only, and that is classified as a single curvatures. When you have a hogging and sagging both, as you can see here, that is classified as a double curvatures. Provide more information now here that moment ratio is a ratio of smaller to bigger moment, and look at the end ratio. Look at the end moment ratio. Now I have taken two examples here to explain the beta m. That is a single curvatures. You can say one end is 100 kilonewton meters and another one, let's say 30 kilonewton per meters. So we need to find the smaller divided by bigger, the smaller divided bigger. When you have a single curvatures, we have a definition for beta m is minus. So when you have single curvature, you have beta m equal to minus value minus 0.3. When you have double curvature, similar example here, we have 100 kilonewton and minus 10 kilonewton meters. That is the example for double curvatures. Now in the case of double curvature, minus become plus, so that is positive 10 over 10. I can say that beta m here equal to positive 0.1. So when you have double curvature, you have positive value. And now the next topic is the moment curvatures. Now I'm going to explain this moment curvatures in the sense that is moment and the x-axis is curvature. My stand for yielding moment, mp stand for plastic moments. Now if I draw the moment versus curvature, when the beam is subjected to the moment has started at 0. Now the way it's classified slender, non-compact and compact word is based on the buckling. So if the beam is buckled before each reaching the yielding moment, or the moment is less than yielding moment, in that case is a slender. You can see the slender one is a thin plate, like a very thin one. That is the when it's made of thin plates, like you can see the thin plates, when it start buckling before it gets for example this thin wall, it will start buckling like this one, then it's become a slender, which does not reach this yield point. So if I draw the stress strain curve of the steel, it does not reach the yield point of the materials, and before reaching the yielding point, it start deforming. Now that's if you are using little bit thicker plates and the thicker cross sections, then it's classified as a non-compact beam. So non-compact section in which you will reach the beam reach the yielding point, but it should not reach the plastic moment. So it's just buckled before reaching to the plastic moment. So it is classified as a non-compact. And if you have compact section, is very strong and thick. So in that case, the beam reached the plastic moments. So it's like this one is weak and this one a little bit stronger than this one, and this one is the most strongest beam that you can say in the general sense. So I have put the quick note here. When you have slender here, m less than, so that is the moment of the beam which is less than my, which is buckled before yielding. Non-compact, beam yields, so beam reached the yield point, so it's reached yield point, but it did not reach the plastic moment, so it does not reach in the plastic moments. And the last one is the compact, when beam reaches the full plastic moment, so it's the strongest. So you can say that the strongest one is the compact, then is the least strongest, then the compact is a non-compact, and the lowest one is the slender cross sections. Now the next one is the last one that we want to look at is the effective section modulus, that is represented by ZE, effective section modulus. So that is a ZE, which is effective section modulus. Now the way effective section modulus is presented here is in terms of B over T. B is the clear width and T is the thickness of the plate. So for examples, this is the flange, This is a top flange, bottom flange, and that is wave. So that is wave, that is I highlighted, and these are the flange. So if you want to see the B over T, if you want to calculate the B over T for the flange, then it's B over T is like this. So you need to take this B over T is the outstand. And for the wave, we have a clear with P equal to T. So that's the definition of B and T. Now the larger the value of this one, so you can see here slender one is a parabolic, this one is linear, this one is linear. When B over T is larger value, meaning that this one is small, so it become larger, then it's the slender one. When your B over T is in this range, you have non-compact. So that is non-compact, and we have a compact section which is strong, which has a lowest B over T ratio. So B over T parameters is very important in the classification of the slender, non-compact, and compact. Thank you very much.